Hello! Let's keep going on our introduction to electronic structure theory. Today I'd like to tell you a little bit about the Born-Oppenheimer approximation and how it leads to potential energy surfaces. So first let me recap our notation for the Hamiltonian. We had this expression, which maybe looks a little scary, but ultimately each term is very understandable. The first term is just nuclear kinetic energy. The next one is electronic kinetic energy. The next one is electron-nuclear attraction. The next one is nuclear-nuclear repulsion. And the final one is electron-electron repulsion. And last time we mentioned we can go to a simplified notation where in atomic units the charge on the electron is 1, 4 pi epsilon naught is 1, h bar is 1, the mass of the electron is 1. And so a lot of the physical constants go away, and this is just easier to write down. And as a further shorthand, just so I can give you a few equations, I'm going to find it convenient to write it this way. Sometimes in physics we use T to mean a kinetic energy operator. So here I'll mean the kinetic energy of the nuclei, subscript n, and their coordinates will be denoted by this vector bold R. So this just collects all the Cartesian coordinates of all the nuclei into one big vector. And then similarly, I can collect all the Cartesian coordinates of all the electrons in this bold little r, and it's T sub e for electrons. And I put little hats on these to remind me that these are mathematical operators and they're taking second derivatives, which is important. And then the next term I'll call VEN. It's a potential energy between the electrons and the nuclei. It depends on the coordinates of the electrons and the coordinates of the nuclei. The next one is a nuclear-nuclear repulsion energy, VNN, and then finally VEE for the electron-electron repulsion energy. The last three are potential terms, V, and the first two are kinetic energy terms, T. All right. Now, not surprisingly, the Born-Oppenheimer approximation is named after Born and Oppenheimer, Max Born and the famous J. Robert Oppenheimer. And let me give you the hand-wavy version of this approximation first, and then I'll show a few details because it'll only take a few slides, and it's kind of interesting how this all really works out. But here's the hand-wavy version first. The nuclei are much more massive than the electrons by a factor of at least 2,000 to 1, frequently more than that. And so therefore, it shouldn't surprise you that the electrons zip around very much faster than the nuclei do because they're much lighter. Okay? So to a first approximation, what we're going to do is say that the electrons can rearrange themselves almost instantly anytime the nuclei move, okay? Or in other words, if you're an electron, you're so fast that from your point of view, it seems like the nuclei are frozen, okay? So sometimes people talk about the clamped nuclei or the frozen nuclei approximation with respect to what the electrons are doing. Okay, that's the basic idea. And I can show you a little more than the basic idea with a few equations. So here is this equation I had a minute ago for the expression for the Hamiltonian in terms of these simplified notations with T's and V's. And so what do I do in the Born-Oppenheimer approximation? Well, procedurally, what I do is I solve for the motions of all the electrons. What are the electrons doing? Where are they going? How are they described in terms of their matter wave or the wave function psi? And from their point of view, I'm going to temporarily freeze the nuclei. So the nuclei are fixed at certain Cartesian coordinates, and then I solve for what are the electrons going to do if the nuclei were there and not moving. Okay? Now, then, if I do this, the nuclear coordinates are, in the middle of this procedure, while I'm solving for the electron motions, become not free variables, not independent variables, but actually fixed parameters. I've lock them down, so I just have a list of what these coordinates are, but they're not moving, so they're constant. Now, VEN, of course, depends on R, and now I'll denote this kind of as a parametric dependence. VEN is a function of the electronic coordinates R, and I'll put a semicolon and then capital R to try to remind myself that while I'm in the middle of solving for the electronic motions, capital R is now a constant, or a set of fixed parameters, rather than independent variable. And then I'm also going to basically temporarily ignore the kinetic energy, because for right now we're pretending the nuclei are frozen in place, and so they have no kinetic energy. Of course, really they do have kinetic energy, but we're setting that aside for right now. Okay, so I'm going to draw a line through my kinetic energy operator, and I'm going to change this comma to a semicolon to remind me capital R is now a fixed parameter. This I'm going to call the electronic Hamiltonian now, the one where I've dropped the first term and then had fixed coordinates, capital R. And if I solve now h psi equals e psi with this Hamiltonian, the electronic Hamiltonian, that will give me what the electrons are doing, and I'll get an electronic wave function and an electronic energy, okay? And I could write this way. Electronic Hamiltonian has an eigenfunction psi that when I act h electronic on psi, I get psi back times a constant, which is now the electronic energy, not the total energy, because I don't have the nuclear kinetic energy part, so it's not the full energy, it's just the electronic part. And what is that electronic Hamiltonian? Well, it's just what I wrote above. Cross out the first thing, put a semicolon there. So I get those 4 terms now instead of 5 terms. Okay, that's what I do to get the electronic wave function. Now, let me say a word about the nuclear kinetic energy. I had that included in my electronic Hamiltonian, and that might seem odd to you because, after all, it's not an electronic term. There are no electrons there, there are no electron coordinates there, there's no charge on electron there. It's what the nuclei do. They repel each other, and that's it. And capital R, again, is a constant, or a set of constants. And so the nuclear repulsion is a constant. So why include that in the electronic Hamiltonian? Basically, it's just traditional to do this. Okay? So it is a constant for a given set of parameters, capital R. And now what happens if I add a constant to a Hamiltonian? Well, if you learned a little quantum mechanics, you know the answer to this. If you don't, let me try to explain it. If you add a constant to a Hamiltonian in quantum mechanics, then all you do is you shift the eigenvalues, or in this case the energies. The eigenfunctions, the wave functions, don't change. They don't care if you've added a constant or not to the Hamiltonian. And I can show you this in 3 or 4 lines here, so let's do that. Suppose I originally solved for h I equals e psi. And then suppose I say, well, oops, no, let me add a constant to the Hamiltonian. How does that change my answer? Well, I can break this up into 2 terms, h times psi and c times psi. C is constant. And then h times psi is e times psi, my original solution, so I can do that. And then I can now pull psi back out to the right, and I get this. And what does that mean? Well, I started with h plus c acting on psi, and I wound up getting psi back times a constant, and that constant is e plus c. So the eigenfunction is the same for h, or h plus c, because either way I act the operator on it and I get the thing back times a constant. Here I got a constant of e sub I, here I got a constant of e, I guess this should be e sub I actually, plus c. And so I shift the eigenvalue up by c, and the eigenfunctions stay identical. So in other words, it's trivial to include if I want, and traditionally we do. Okay, now let me just mention a practical concern real quick for computational chemists. VNN, the nuclear repulsion energy, is very sensitive to these parameters, capital R, where are the nuclei. And so it's a good diagnostic tool if you're trying to reproduce something from the literature and you compute the nuclear repulsion energy, and if you're lucky enough that some paper reported their nuclear repulsion energy, and if you don't match it, then you probably have a different set of coordinates for your atoms. And so this is a very easy thing to check that requires, hardly any calculation time. If these things don't match, then no, you're not using the same geometry. And if you're not using the same geometry, you can't match the polarizability or the dipole moment or the electronic energy or anything. So this is a good quickie thing to check first that requires essentially trivial calculation. And I already mentioned my next point. Okay, so let me give a brief intro into the Born-Oppenheimer Mathematics. This is a little more advanced than the basic idea, but I think it's very interesting, and it will only take a few slides. So if you're interested in some more details, let me go through those. And then after I do this, I'll pick back up with the basic intro to what potential energy surfaces really are and how they come out of the Born-Oppenheimer approximation. All right, so I said I'm going to solve my electronic Schrodinger equation to get the electronic energies and the electronic wave functions. Okay? Now, the full wave function, of course, is not this. This is just the electronic part. So what's the full wave function? Well, the full wave function I can expand in a basis, and I will make that basis the electronic wave functions. Okay? So they're going to form a set of functions that I could use as basis functions. K is now going to index the different solutions to the electronic Schrodinger equation. Like any eigenvalue equation, this electronic Schrodinger equation has more than one solution. And so I'll put a subscript to say which solution am I talking about. So I sum over all the electronic states, and I need a coefficient in front of each of those. And the coefficient may change depending on how capital R changes. And so I'll denote that the coefficient depends on capital R. And I'll write it this way. I'll say there's a different coefficient in front of each of these, and so I'll call them chi sub k. And you notice this coefficient, because it does depend on the coordinates of the nuclei, you could interpret this as a nuclear wave function. And we'll see that play out here in a little bit. But let me take this expansion and insert it back into the original full-blown h equals e psi. And I'm not going to go through all the details. I'll skip through this and show an equation here or there so you get the gist of it. So after a few steps, I get this kind of nasty looking thing with a bunch of terms I haven't defined yet. I guess I better do that momentarily. I get a bunch of T-like things. These are going to be related to kinetic energy in some way that I'll say a little bit about. Tn of R is just the kinetic energy operator. So he came back, and then I get a couple new terms that I ought to say something about. I get the electronic energy. We already had him, so he's familiar. E is the total energy. Chi, K is this nuclear function that gives me the coefficients in front of the electronic wave functions. So this big expansion equals some other mysterious looking quantities times different chi's with different indices. I'll call them K prime, not equal to K. All right, so this looks like a bit of a mess. However, it turns out this term for real wave functions, and often we deal with real wave functions in computational chemistry, is exactly zero. And these other terms are not exactly zero, but they're usually very small. So let's go ahead and cross all those out. And then that will give me this expression, which doesn't look too infinitely complicated. And what is this going to mean? Well, it's very interesting. I have a bunch of stuff in brackets, and that stuff in brackets multiplies a function and gives the function back times a constant. Well, that's just an eigenvalue equation. Eigenvalue equations are ones where I have an operator times a function gives a function times a constant. So this is a very interesting eigenvalue equation. And notice all the electron coordinates, little r, have disappeared or they're folded inside other things somehow. So this is really an equation having to do with the nuclei and the nuclear coordinates only. And in fact, let's call it the nuclear Schrödinger equation, because this term in brackets, the operator, could be interpreted as a kind of Hamiltonian. Hamiltonians have kinetic energy plus potential energy. That's a kinetic energy, and this is a kind of a kinetic energy. This guy must be playing the role of a potential energy. So this is the potential energy that the nuclei feel. And where did this come from? Well, it came from solving the electronic Schrödinger equation. So you solve for what the electrons do. They do their dance around the nuclei, and that gives you a set of electronic wave functions and electronic energies. And for the ground state, then the electronic energy is a potential energy felt by the nuclei as the nuclei are moving and trying to decide where they're going to go and what they're going to do to give a nuclear Schrödinger equation. Very interesting. Now furthermore, this particular term here, T double prime KK, is also usually very small and frequently neglected. So if you do that, then it literally is a nuclear Schrödinger equation. Kinetic energy plus potential acts on the nuclear wave function to give it back times the full energy. Yeah, where does the potential energy come that the nuclei dance around on? It comes from solving the electronic Schrödinger equation, the electronic energies. That's where it comes from. I'll briefly mention this mysterious T double prime KK term. This is called the diagonal Born-Oppenheimer correction, sometimes called the adiabatic correction. And I mentioned it's small. What does it look like? Well, it looks like this guy. You have kind of like a kinetic energy operator. You have minus, h bar went away because we're in atomic units, 1 over 2 times the mass of the nucleus. We're summing over all the nuclei, so they each contribute. And then I've got a second derivative operator, like in any kinetic energy term. And then on the left and the right, I've got my electronic wave function. And here we're kind of assuming we're on the ground electronic state, okay? And that higher electronic states are not contributing so much to what's going on. Now this second derivative operator, I could break it up into a couple gradient operators and act one on the left and one on the right and get this. And that gives you a hint how you could compute this guy. I could compute the rate of change of the electronic wave function with respect to moving the nuclei. And this is something that we kind of temporarily assume is 0 when we do some other stuff, but here it kind of comes back in this particular term. And I could compute this thing, and that would give me this Born-Oppenheimer diagonal correction. And let me just give you a feeling for how big this thing is or how small it is. At the configuration interaction singles doubles level with a CCPV-TZ basis set, don't worry if you don't know what that is yet, it's 612 wave numbers for water at its normal equilibrium bent configuration. And there's about 350 wave numbers in a kilocalorie per mole, so this is a little shy of 2 kilocalories per mole, which is kind of a lot for a term that almost universally everyone just throws out. So how do people get away with this? Well, it's almost the same if I take water and make it linear, which is of course unnatural, but you know, if you have a high enough thermal energy, water can bounce around and it might occasionally turn almost linear sometimes. And so you might ask, well, what's the energy difference between bent and linear? Well, the Born-Oppenheimer correction is 612 wave numbers for bent, 597 wave numbers for linear, for a difference of only 15 wave numbers. So if all you wanted to know was how much energy does it take to go from bent to linear water, if you ignored the Born-Oppenheimer correction, you'd get a certain answer. If you included it, you get another answer, and those answers would be different by about 15 wave numbers at this particular level of theory. And 15 wave numbers is a tiny, tiny fraction of a kilocalorie per mole. So unless you were going for high accuracy calculations, like you were talking to a spectroscopist friend, this just wouldn't matter. And that's why people normally can get away with ignoring it. Not because it's small, but because when you do energy differences between reactants and products or reactants and transition states, it normally tends to almost cancel. Does it ever affect anything? Well, in one of our papers, we looked at how important it was for the bond length of BH, CH+, and NH, where we can compute this, and it's a tiny, tiny, tiny fraction of an angstrom. So again, unless you're comparing to very high resolution spectroscopy, it doesn't matter for bond lengths. It matters a little bit for vibrational frequencies. These are harmonic vibrational frequencies and how much they shift if you include the Born-Oppenheimer diagonal correction by 2 wave numbers, almost 3 wave numbers, a wave number and a half or so. So on a wave number level, they can matter to harmonic frequencies if you were trying to match an infrared spectrum very exactly. All right, now let me set aside that excursion into a little bit more detail about Born-Oppenheimer approximation and come back to some basic concepts. So we talked about how the nuclei move around on a potential generated by the electrons via the Born-Oppenheimer approximation. And so that's ultimately where potential energy surfaces come from mathematically, because this electronic energy depends on the nuclear coordinates, and it's different for each different arrangement of nuclear coordinates. Then it's an energy that varies across different configurations of nuclei, and that is the potential energy surface felt by the nuclei. Now, a few more details about this and considerations. First off, if I have some molecule like water or benzene or whatever, if I move that benzene in empty space, then the potential energy that the nuclei feel shouldn't matter, because that particular degree of freedom doesn't matter as long as I'm not in an electric field or nearby other molecules or something like that. The electronic energy should only depend on the internal structure of the molecule, like how close are the bonds and things like that. How many degrees of freedom are there that then shouldn't matter to the electronic energy? Well, each molecule, I could translate it in space in the x direction or the y direction or the z direction. And so there are 3 degrees of freedom for translations that shouldn't affect the internal structure of the molecule or its electronic energy. And most molecules, there are 3 rotational degrees of freedom, because I could imagine 3 axes about which I could rotate the molecule. And if I rotate a molecule, again, that doesn't change its internal structure or its electronic energy. Now, if it's a linear molecule, then that one only has 2 degrees of freedom, because if I spin a linear molecule about its own axis, then that doesn't do anything, okay? So that doesn't count as a degree of freedom. But I get a legitimate rotation if I spun around, this way, or if I spun around this way. Those are actual rotations. So linear molecules only have 2 rotational degrees of freedom. Nonlinear molecules have 3. So therefore, if I had n atoms, then there are 3n minus 6 internal degrees of freedom. You might call them vibrational degrees of freedom. And if it's a linear molecule, there are 3n minus 5 vibrational coordinates. And the electronic energy will change if I change any of those vibrational or internal coordinates. Therefore, the potential energy is a function of 3n minus 6, occasionally 3n minus 5 coordinates. And let me just give a few examples of potential energy surfaces. So here is a potential energy curve, because there's only 1 degree of freedom for the C2 molecule. Now C2 has 2 atoms, so 3n minus 6, oops, this one's linear, 3n minus 5 would then be 3 times 2, which is 6, minus 5 is 1. 1 vibrational degree of freedom. And of course, for a C2 molecule, or any diatomic molecule, there's 1 degree of freedom for a vibration, the regular bond vibration. So here I'm plotting the potential energy curves versus this stretching coordinate, okay? And I've got 3 curves, so this is interesting. I've got a black one and a blue one and a red one. Why is that? Well, again, you can have multiple solutions to the electronic Schrodinger equation, so you have multiple electronic states. And here are 3 of them. In fact, there can be more. I didn't draw all the possible ones. These are so-called singlet states, so they have a superscript 1 on the so-called term symbol, denoting the symmetry of these states. On the left, you have a superscript that tells you sort of the spin symmetry. These are all so-called singlets because there's a 1. And then the rest of the symbol tells you something about the spatial symmetry of the electronic state, which I won't get into right now. But the black one is the ground state because it's the lowest in energy. Well, it actually crosses this red one. So if I'm around here in bond length, then the black one is the ground state. But if I am up here and I've stretched it out, say to 2 angstroms, then the ground state would flip over to this red state, a so-called singlet delta G state. So that's interesting. And then it gets really close to the black one. So there's not a lot of difference there. The blue one is a little different, so it's a higher lying, again, singlet sigma G plus state. So for sure, you can have multiple potential energy surfaces. Normally in chemistry, we talk about just the lowest energy one, unless you're doing something like highly vibrationally excited molecules or a very reactive system where maybe you hit it with a laser and you pump in some energy and you can access excited states. And I've got to talk about excited states that you can catch later. But a lot of chemistry, we just consider the ground state, which here is mostly the black one. Now, what are some features of potential energy surfaces? So here I'm showing a more generic diagram. And suppose I have some reaction where I started off at some reactant in a certain geometry, and then I go uphill in energy, and then I go downhill in energy to a product. In this particular reaction, the product is lower than the reactant. That doesn't always have to be the case, but it is in this particular diagram I'm showing you now. So this would be an exothermic reaction because I wind up in a more stable situation and energy is conserved. So where does it go? It comes off as heat, and so it's exothermic because heat would be generated somehow. And what's the x-axis here? The y-axis I've already indicated is energy. The x-axis here is some generic reaction coordinate, okay? Which really is some path through this 3n minus 6 dimensional space that most efficiently leads from reactant over the transition state to product. Sometimes you might call this a minimum energy path. And a lot of those details get glossed over if you see a diagram like this in a freshman chem book or an organic chem book. But you're really walking through 3n minus 6 dimensional space, and this is just a simplified cartoon of that process. Now notice the reactant and the product are both minima here in this diagram. So that's important. And then the transition state is an energy maximum, okay? So these things have different concavity or convexity. All 3 are called stationary points in computational chemistry. A stationary point, all that means is that the derivative of the energy with respect to some relevant coordinate of nuclear motion, or a vibrational coordinate, is 0 at the stationary point. So you can see that the derivative here is 0, the derivative here is 0, the derivative here is 0 with respect to x. Now locally, around these 2 minima, and in fact even around the transition state, the energy looks kind of quadratic. They look kind of like parabolas, either a parabola going up or a parabola going down, depending on if you're at a minimum or a transition state. It's kind of a quadratic looking function, okay? And that's very helpful in modeling what the vibrational motions are near these points, particularly the reactants and products. Now, if you took this as a simplified view of what the local energy around these stationary points looked like, then this should remind you of the famous harmonic oscillator problem from classical physics, where a potential energy is quadratic in whatever the relevant independent variable is, okay? And if you remember something about harmonic oscillator, you might remember that the solutions to motion on a potential like that are sine or cosine functions with a period that's proportional to the square root of this constant k divided by the mass, or in this case, the reduced mass, mu. So this is kind of a harmonic oscillator model, and then you know the harmonic frequency of vibration. And k for a reactant or a product or any minimum is a positive number, and so the square root of a positive number divided by mu, which is a positive number, is a real number. So you get real vibrational frequencies at a minimum. However, if I'm at a transition state, then there k is negative because the potential energy surface is kind of upside down there. And so if k is negative and I put it inside a square root symbol, then I get an imaginary number for omega. And so therefore, that's why we talk about imaginary frequencies in quantum chemistry. If you do the vibrational frequency calculation and get imaginary frequencies, then it means you're at some kind of a saddle point where you're at a local maximum in at least one dimension. Now here's maybe a more realistic diagram that gives you a sense of what a potential energy surface looks like. So here I'm plotting the energy as a function of two coordinates. Here they're called generalized coordinate Q1 and Q2, okay? And in the bottom is a nice contour diagram, if you like contour diagrams. And on the top is more of a kind of a depiction of what it would look like in 3D. Of course, it's a 2D drawing, obviously. And here, imagine I start here. This is the reactance, or down here. Here it is in the contour diagram. And it's very shallow, but I go up in energy a little. It kind of looks like you're going down, really, but you go up slightly in energy to get to this transition state, and then you fall downhill to this intermediate. It's a local minimum. Then I go uphill slightly, and then I fall down into this local minimum, and this is the products. So in fact, this is the global minimum. The intermediate's a local minimum. The reactant's a local minimum. This is maybe a little easier to see in the contour diagram. Certainly that's a minimum, that's a minimum, that's a minimum. Here, you're definitely not at a minimum, nor are you here. And so these are the transition states. But notice, although the transition states are local maxima, if I'm coming downhill here or downhill here, they're minima with respect to the orthogonal coordinate. So along this direction, which is what, the Q2 direction, the transition state's a minimum. And likewise here, this transition state, as I'm falling down this way, is a minimum with respect to this other coordinate, Q1. So transition states are a maximum along exactly one coordinate and a minimum along all other coordinates. That's the definition of a transition state. And here you can see this potential energy surface has what? 3 minima and 2 transition states. So that's interesting. The ideal reaction path, the path that you would ideally follow with a minimum energy cost to get to reactants to products, is called the minimum energy path. And you can see that's this line that I've traced, okay? So I could get from reactants to products if I kind of bounced over here and came down this way, but that would take more energy to go over this bump than it would be to follow down this path. So that's why this is the minimum energy path, the line. I can find out what are the minimum energy paths for a particular reaction by using something called intrinsic reaction coordinate analysis, IRC. And this is typically something you would do after you've already located, say, the reactants and products and the relevant transition states. Okay. So I think I've kind of already mentioned this, but let me just reiterate the first couple points and introduce one more term. If I have a stationary point where the gradient goes to 0, the gradient of the electronic energy with respect to nuclear coordinates, then there are three situations of how to classify that stationary point. It could be that it's a minimum where no matter which direction I head in, the energy goes up. So it's a local minimum. All the vibrational frequencies will be real if I compute them. And this corresponds either to a stable species or at least quasi-stable. So on the previous graph I had an intermediate, which is locally stable, but then if I kind of kick the system a little bit, you'll fall downhill. Transition states, we mentioned they're a minimum in every direction except for one, and then it's a maximum in that direction. So it's a barrier going from one local minimum to another. And then I didn't mention this yet, but I should just point out, you can have a situation where you're at a so-called higher order saddle point. And that's just a case where the gradient is zero, so you're at a stationary point, but you're at a maximum in more than one dimension. And if you're at a maximum in more than one dimension, you're not eligible to be called a transition state. You'll be called higher order saddle point. These tend to not have much real consequence in terms of chemistry, but they're there on the potential surface, and if you had molecules bouncing around like crazy with enough energy, they may cross in the vicinity of these things. Okay. And finally, the Hessian index is just a number. It's the number of imaginary vibrational frequencies you compute. If your Hessian index is 0, then you're at a minimum. If it's a 1, you're at a transition state. If it's more than 1, you're at a saddle point. Next time, we'll talk about a quick tour of the various kinds of electronic structure methods: Hartree-Fock, DFT, semi-empirical methods, electron correlation methods. I'll introduce them all quickly, and then we'll have talks in more detail about those later on.